Welcome! In this video, we will solve LeetCode problem number 369, titled +1 linked list. This problem challenges us to increment the number represented by a singly linked list, where each node contains a single digit. We'll explore the steps to solve it efficiently and discuss the algorithmic considerations. Let's dive in. In this problem, you are given the head of a non-empty singly linked list. This linked list represents a non-negative integer, but there's an important detail: the digits of the number are stored in reverse order. For example, the least significant digit comes first, followed by the more significant digits. Your task is straightforward: you need to add 1 to the number represented by this linked list and return the resulting linked list, keeping the digits stored in the same reverse order. The input to your function will be the head of this linked list, where each node contains a single digit. The output should also be the head of a linked list, which represents the new number after adding 1. Let's explore a few examples to understand the problem better. In the first example, the input linked list is 1, 2, 3. This list represents the number 321, since the digits are stored in reverse order. When we add 1 to 321, the result is 322. To represent this in the same reverse order, the output linked list would be 4, 3, 2. Now, consider the second example with the input 999. Here, the linked list represents the number 999. Adding 1 to 999 gives us 1000. Notice that this result introduces a new digit, which means the output linked list will be 0001 to maintain the reverse order. In a simpler case, like the third example, the input linked list is 0. This represents the number 0. Adding 1 to 0 results in 1, and the output will be 1, which is the reverse order representation of the number 1. Now, let's review the constraints for this problem. First, the number represented by the linked list will not have leading zeros, except for the special case of the number 0 itself. The length of the linked list can range from 1 to 10,000 nodes, so your solution needs to handle very large lists efficiently. Additionally, each node's value will always be a single digit between 0 and 9. There are a few edge cases you'll need to handle carefully. For a single node linked list, like 0, your solution should correctly output 1. Another important scenario is carry propagation. For example, when the input is 999, the solution must handle carrying over across multiple digits, producing 0001. Similarly, if the input contains all zeros, such as 000, the output should be 1000. Finally, for a linked list with the maximum possible length of 10,000 nodes, your algorithm must be efficient enough to process the input within the given constraints. These edge cases ensure that your solution is robust and handles all possible inputs correctly. To solve the +1 linked list problem, we need to increment the number represented by a singly linked list where the digits are stored in reverse order. This means the least significant digit, or the ones place, is at the head of the list. The challenge lies in efficiently propagating the carry without reversing the list multiple times. One approach we considered is the brute force method of reversing the list twice. The intuition here is to reverse the list so that the digits are in the correct order, with the most significant digit first. Once reversed, we can add 1 to the number, handle any carry as we traverse the list, and then reverse the list again to restore its original order. While this approach is straightforward and easy to implement, it involves modifying the list structure twice, which adds overhead. The time complexity is O(n), because reversing the list twice and performing the addition each take linear time, but this extra manipulation can be inefficient in some scenarios. Another approach we considered leverages recursion for backtracking. Using recursion allows us to traverse to the end of the list, where the least significant digit is located, and then perform the addition. As the recursion unwinds, the carry is propagated back to the previous nodes. If there's a carry left at the head after processing all nodes, we handle it by creating a new node at the front. This method avoids reversing the list entirely and is quite elegant. The time complexity is O(n), because we visit each node exactly once. However, the space complexity is also O(n), due to the recursion stack, which can become a concern for very large linked lists. While this approach is conceptually clean, the memory overhead from recursion makes it less ideal for larger inputs. Finally, we explored a third method, which uses an iterative two-pass strategy. This involves identifying the rightmost digit that isn't a 9, known as the pivot, and using it as the key point for carry propagation. We ultimately chose the iterative two-pass approach because it is both efficient and simple to implement. This method requires only 2 linear passes through the list and uses constant space, making it the optimal choice for this problem. It avoids the recursion overhead of the backtracking approach and the repeated reversing of the brute force method. The key insight, or aha moment, was recognizing that the position of the rightmost non-9 digit determines how the addition propagates. By focusing on this pivot and the digits that follow, we minimize the changes needed. For example, if the pivot is increment, all subsequent digits are simply reset to 0. Edge cases, such as when all digits are 9, require creating a new head node, but these can be managed with clear checks. Additionally, the observation that carry only propagates forward allows us to make this process efficient and focused. When comparing the 3 approaches, the trade-offs become clear. The brute force method of reversing the list twice is simple and intuitive but requires modifying the list structure twice and adds unnecessary overhead. The recursive approach is elegant and avoids reversing the list, but it comes with the downside of O(n) stack space due to recursion, which is not ideal for very large lists. In contrast, the iterative two-pass approach is the most balanced solution. It achieves O(n) time complexity and O(1) space complexity, making it both efficient and scalable. While it requires careful handling of edge cases, such as when all digits are 9, these challenges are manageable and do not outweigh the benefits. For this reason, we determined that the iterative approach is the most practical and effective strategy to solve this problem. To solve the problem of adding 1 to a number represented by a singly linked list, we start by reversing the linked list. This is necessary because the least significant digit, or the ones place, is at the head of the list, making it difficult to handle addition and carry propagation directly. By reversing the list, we can process the digits from the least significant to the most significant, which simplifies the addition process. The reversal is performed using 3 pointers: previous, current, and next. Initially, previous is set to null, current points to the head of the list, and next temporarily holds the reference to current.next. We iteratively update the links so that current.next points to previous, effectively reversing the direction of the list. Once the current node becomes null, the reversal is complete. After reversing, we proceed to add 1 to the number. Starting from the head of the reversed list, we add 1 to the value of the current node. If the result is 10 or greater, we update the node's value to the remainder when divided by 10, and carry over the value of 1 to the next node. If no carry is generated, we simply update the node's value and continue. This process ensures that the addition is handled correctly, digit by digit, propagating any carry as needed. If, after processing all the nodes, there is still a carry of 1 left, we need to handle this by adding a new node with the value 1 at the end of the list. This accounts for cases like adding 1 to 999, where the result requires an additional digit, turning it into 1000. Once the addition and potential carry propagation are complete, the next step is to reverse the linked list back to its original order. Doing this restores the most significant digit to the head of the list, ensuring that the final representation of the number is correct. Lastly, we return the updated linked list, which now represents the number increment by 1. These steps are designed to work seamlessly with the constraints of a singly linked list, ensuring that we handle all cases efficiently and correctly. Reversing the list simplifies the addition process, but why is this necessary? When adding 1 to a number, it's easiest to start from the least significant digit since any carry generated needs to propagate to the higher order digits. In the original order, this is not directly possible because the least significant digit is at the head. By reversing the list, we can traverse the digits in the correct order for addition. Carry propagation is a critical aspect of the algorithm. For example, when adding 1 to 999, each digit update generates a carry, requiring us to propagate it through all nodes and eventually create a new node for the carry. Handling edge cases is also important. For an empty list, we simply return a new node with the value 1, as there are no existing digits to process. For numbers like 999, where all digits are 9, the algorithm ensures that the carry is correctly propagated and a new node is added to handle the overflow, resulting in the correct representation of 1000. The singly linked list is the primary data structure used to represent the number. This is given in the problem and is well suited for operations like reversing and node manipulation. Using pointers such as previous, current, and next allows us to efficiently reverse the list and traverse through it during the addition process. When analyzing the complexity of the algorithm, we find that it is highly efficient. The reversal of the list is performed in n time, where n is the number of nodes. Adding 1 to the number and propagating the carry also takes n time, as each node is visited once. Reversing the list back to its original order adds another n. Therefore, the total time complexity is n. The space complexity of the algorithm is 1, because we use only a constant amount of auxiliary space, relying on pointers for all operations rather than additional data structures. This makes the solution both time and space efficient for the given problem. Here, we define our list node class to represent each node in the linked list, along with a solution class that contains the method +1. The +1 function is where we perform the operations needed to increment the linked list by 1. To start, we define a helper function called reverse_list, which takes a node as input and reverses the linked list. This is done by iterating through the list, adjusting the next pointers to point to the previous node, and finally returning the new head of the reversed list. The first step in our algorithm is to reverse the linked list using this helper function, which allows us to process the least significant digit first. After reversing the list, we initialize a variable carry to 1, representing the digit we want to add to the number. We then start traversing the reversed list using a current pointer. For each node, we add the carry to its value. If the resulting value is less than 10, we reset the carry to 0 because no further propagation is needed. However, if the node's value becomes 10 or greater, we set its value to 0 and continue to the next node, ensuring that the carry is propagated. If we reach the end of the list and there's still a carry, we create a new node with a value of 0, which allows us to extend the list and handle cases like turning 999 into 1000. Once the addition is complete, the final step is to reverse the linked list back to its original order using the reverse_list function again. This restores the structure of the list so that the most significant digit is at the head. Finally, we return the modified linked list, which now represents the increment number in its original order. Here, we start with the definition of the list node class, which represents a single node in the linked list. Each node contains an integer value, val, and a reference to the next node, next. The constructor initializes a node with a given value and sets next to null. Below that, we define the solution class, which will house our methods. The first method, reverseList, is a helper function to reverse a linked list. This is crucial because our approach involves reversing the list, performing the addition, and then reversing it back. Inside this method, we initialize previous to null, which will eventually point to the new head of the reversed list. The while loop iterates through the list, and for each node, we temporarily store the next node, redirect the current node's next pointer to previous, and then move both previous and head one step forward. After the loop, previous holds the reversed linked list, which we return. Finally, the +1 method begins by reversing the input linked list using this helper function. Now that the list is reversed, we proceed to step 2, adding 1 to the number represented by the linked list. We initialize carry as 1, since we need to add 1, and use a while loop to traverse the reversed list. For each node, we add the carry to its value. If the resulting value is less than 10, it means no carry is needed, so we set carry to 0 and exit the loop. Otherwise, we set the current node's value to 0 and check if there's a next node. If not, we create a new node with a value of 0 to handle any remaining carry. After completing the addition, step 3 involves reversing the list back to its original order using the same reverseList method. This ensures the digits are in the correct sequence. Finally, we return the head of the modified list, which now represents the original number +1. The problem here is to add 1 to a number represented as a singly linked list, where each node contains a single digit. The most significant digit is at the head, which makes direct addition a bit tricky. Instead of converting the linked list into an integer, we solve this problem in place by reversing the list to make addition easier, performing the addition digit by digit, and then reversing the list back to restore the original order. For example, if the input is the linked list representing 123, we begin by reversing it. This process involves iterating through the list, updating pointers at each step. Starting with the initial state of 1-2-3, the first iteration updates the first node to point to null. On the second iteration, the second node points to the first, and so on, until the entire list is reversed, resulting in 3-2-1. This reversal sets the stage for the addition operation. With the linked list now reversed, the least significant digit is at the head, making it easier to add 1. Starting with the first node, which has the value 3, we add 1 to get 4. Since there's no carry, we simply update the node's value and move to the next node. The second node, with value 2, remains unchanged, as does the final node with value 1. This completes the addition, leaving us with the updated reversed list 4-2-1. To restore the number to its original order, we reverse the list again using the same process as before. This gives us the final list 1-2-4, which represents the number 124. The output for this example is 1, 2, 4. Now let's look at a slightly more complex example, where the input linked list represents 999. After reversing, the structure of the list remains 9-9-9, but the addition process introduces carry propagation. Starting with the first node, we add 1 to the value 9, resulting in 10. The node's value is updated to 0, and the carry is propagated to the next node. Repeating this process, the second and third nodes are also updated to 0, with the carry continuing forward. Since there's no next node after the third, we create a new node with the value 1 to account for the final carry. This results in the updated reverse list 0-0-0-1. Reversing this list back gives the final result 1-0-0-0, representing the number 1000. The output here is 1, 0, 0, 0. In this simpler example, the input linked list represents the number 0. Reversing the list doesn't change its structure, so it remains as 0. When we add 1 to the first node, the value becomes 1, and since there's no carry, no further updates are needed. The updated reversed list is simply 1. Reversing it back gives the same result, 1. Thus, the output for this example is 1. This demonstrates how the solution handles edge cases, such as a single-node linked list. To summarize, reversing the linked list simplifies the addition process by allowing us to start from the least significant digit. Carry propagation is handled seamlessly by iterating through the list and updating nodes as needed, even creating a new node if the carry extends beyond the last digit. Finally, we reverse the list again to restore its original order. This approach effectively solves the problem in place without converting the list to an integer, ensuring efficiency and correctness for all input cases. To analyze the time complexity of our solution, we can break it down into 3 main steps. First, we reverse the linked list. This reversal involves iterating through the entire list once. If the length of the linked list is n, this step requires n iterations, where each iteration takes constant time to update pointers. As a result, the time complexity for reversing the list is O, n. Next, we add 1 to the number represented by the linked list. This step involves traversing the nodes to handle the addition, including any carry propagation. In the worst-case scenario, such as when the input is all 9s like 9, 9, 9, we may need to traverse the entire list. Since adding 1 to each digit is a constant time operation, this step is also O, n. If a new node is created for the carry, such as when 999 becomes 1000, that operation is constant time and does not impact the overall complexity. These 2 steps together ensure we're working within linear time so far. Now, we reverse the linked list again to restore its original order. This step is identical to the first reversal. We iterate through the list, updating pointers, which takes O, n, time. When we look at the overall time complexity, we see that each of the 3 steps reversing the list, adding 1, and reversing it again takes O, n, and because they're performed sequentially, the total time complexity is O, n, plus O, n, plus O, n, which simplifies to O, n. Shifting focus to space complexity, we see that the reversal process operates in place, modifying pointers directly, which means it uses constant space, or O1. Similarly, the addition step does not require extra space, even when a new node is created due to carry, as this operation is constant in space. Importantly, since there are no recursive calls in our solution, we avoid any additional space usage from the call stack. With this in mind, the overall space complexity of the solution is 1, because it uses only constant extra space. Now, let's evaluate the time complexity across best, average, and worst cases. In the best case, the carry propagation ends after adding 1 to the first digit, such as when 1, 2, 3 becomes 1, 2, 4. Even in this scenario, the list still needs to be reversed twice, which makes the time complexity n. For the average case, carry propagation typically occurs for some portion of the list, but the complexity remains n. In the worst case, carry propagates across all n nodes, such as when 9, 9, 9 becomes 1, 0, 0, 0. Despite the additional work for carry propagation, the time complexity is still n. This demonstrates that the time complexity is consistent across all cases, as the 3 sequential steps dominate the runtime. Finally, let's compare our optimized approach to a naive solution. A naive approach might convert the linked list to an integer, perform arithmetic, and then reconstruct the list. While this approach has a time complexity of n, it also requires n space to store the integer representation. On the other hand, our optimized solution avoids this conversion and operates entirely in place. It achieves the same time complexity of n, but reduces space complexity to 1. To solidify this, we can look at a mathematical proof of the big O. The time complexity is dominated by the 3 traversals of the linked list, each taking n. Since constants are ignored in big O notation, the overall time complexity is n. The space complexity, remaining 1, is minimal because no extra data structures are used, and all operations are performed directly on the linked list. This highlights the efficiency of our optimized approach. When solving the +1 linked list problem, there are several common mistakes to watch out for. First, not handling carry propagation correctly is a frequent issue. For example, consider the linked list representation of the number 999. If you forget to propagate the carry through all the nodes, you might end up with an incorrect result like 900 instead of the correct 1000. This mistake highlights the importance of ensuring that the carry is propagated all the way to the most significant digit. Next, modifying the linked list in place without considering edge cases can lead to problems. Scenarios like an empty list, or a single node with the value 9, require special handling. Without accounting for these cases, your solution could result in runtime errors or incorrect outputs. Another issue is reversing the list incorrectly. While reversing can simplify the addition process, failing to restore the list to its original order afterward can leave your result in an unexpected format, which might not be acceptable depending on the problem constraints. These pitfalls emphasize the need for a thorough and careful approach when implementing your solution. Now, let's look at a few more common mistakes and insights to strengthen your understanding. Inefficient traversal is another potential pitfall. If your solution involves traversing the list multiple times unnecessarily, it increases time complexity. This can often be avoided by combining operations into a single traversal. Additionally, allocating unnecessary nodes is a mistake to avoid. For instance, creating new nodes for every digit, even when it's not required, leads to inefficient memory usage and makes the implementation overly complex. Moving on to some interview insights, it's helpful to recognize that this problem is a variation of the +1 problem for arrays, which is LeetCode number 66. Understanding this connection enables you to apply similar strategies to the linked list version. Also, be sure to focus on edge cases like an empty list, all lines, or a single node, as these are often discussed in interviews. Finally, be prepared to explain the trade-offs in your approach. For example, if you reverse the list to simplify the addition, you should justify why this trade-off is acceptable. Aiming for an optimal solution with n time complexity and 1 space complexity is a good practice, as this aligns with what interviewers typically expect. To deepen your understanding of the +1 linked list problem, it's useful to explore related problems. For example, LeetCode number 2, add 2 numbers, is a similar challenge where you deal with linked list representations of numbers, but instead of incrementing, you're adding 2 numbers. Another closely related problem is LeetCode number 66, plus 1, which is essentially the array-based version of this task. Recognizing how digit manipulation works in arrays can help you draw parallels to linked lists. Additionally, LeetCode number 445, add two numbers to, involves adding numbers stored in reverse order, where the most significant digit comes first. This problem also ties into carry propagation and linked list manipulation, making it an excellent complement to the plus 1 linked list problem. Finally, LeetCode number 234, palindrome linked list, introduces the concept of reversing a linked list, which is a common pattern across multiple linked list problems. Familiarizing yourself with these related challenges not only reinforces your understanding of linked list operations but also helps you recognize patterns that can be applied to a variety of problems. Let's discuss some alternative approaches and their trade-offs. One popular method is to reverse the linked list. By reversing the list, you simplify carry propagation, as you can process the digits from least significant to most significant. However, the trade-off here is that you'll need extra space and time to reverse the list twice, once at the beginning and again at the end to restore the original order. Another approach is to use recursion. By traversing to the end of the list recursively, you can propagate the carry back up the call stack. This technique is elegant and avoids explicit reversing, but it comes with higher memory usage due to the recursion stack, which can be a limitation for very deep lists. Lastly, there's the two-pass solution. In the first pass, you calculate the length of the list and identify the last non-9 digit. Then, in the second pass, you handle the carry propagation. This method reduces unnecessary operations by focusing only on relevant parts of the list, but it does require two traversals, which might not be ideal for extremely large linked lists. Each approach has its strengths and weaknesses, and the choice depends on the problem constraints and your priorities, whether that's minimizing space usage, optimizing for time, or keeping the implementation simple. Great job! To summarize, we tackled the plus 1 linked list problem by reversing the list, performing the addition, and reversing it back. Key takeaways include mastering linked list manipulations and carry propagation. Thanks for watching. If you enjoyed this, please like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!